Assalamualaikum and hi everyone. We are from Group 19. We would like to present our integrated design project of methanol production plant. So our group members consist of me, myself, Siti Nurzuliha binti Makhtar, Mohamed Ilyas bin Marzuki, You Teoh, Nur Maisarah binti Kusdi, and Shireen Natasha binti Mohamed Hakimi.
So in this presentation, we'll be discussing about the introduction of project, process flow diagram, thermodynamics, which is the high-speed flash calculation, and last but not least is separation process 1, which is to propose a design of distillation column for methanol purification.
I will be presenting the introduction chapter for this project. In this project, we will discuss the methanol production. Methanol is an important building block in our lives as it is used to produce many other chemicals according to our needs. Methanol, by description, is very light, colorless liquid at room temperature. It goes by the chemical formula of CH3OH, and it belongs to the alcohol group because it has the hydroxyl substituent. Methanol is a polar substance due to the presence of oxygen atom, which cause an inward dipole. Methanol is also very volatile, liquid, and quickly evaporates even at room temperature. Methanol is also extremely flammable and must be handled with care and away from fire hazards to avoid any unwanted incidents. Next, we will look at the production method. Methanol production is done by gas synthesis. Synthesis gas, or also known as syngas, is a mixture of carbon monoxide and hydrogen gas that is used as fuel gas, but is produced from a wide range of carbonaceous feedstocks and is used to produce a wide range of chemicals, in this case, methanol. The general chemical equation for the process is CO plus H2, which yields our desired product, methanol. The reaction is catalyzed by copper-zinc catalyst. The presence of the copper-zinc catalyst allows us to conduct the reaction at a significantly lower pressure and temperature. The pressure is ranged between 50 atm to 100 atm, and the temperature is set at 250 degrees Celsius. Without the catalyst, we would have to conduct the reaction at 300 atmosphere, which with the temperature ranging from 300 degrees Celsius to 400 degrees Celsius, which will increase the cost and undesirable by any means. Next, for the plant capacity, our plant capacity is aimed at producing 50% of Malaysia's annual methanol production. The plant will be based at Batu Gajah, Perak. To meet this goal production, we would have to produce 630,000 metric tons of methanol annually. That means 1.6 billion kilogram of methanol daily, or 66,000 kilogram per hour. For the instruments used for this methanol production process, we will be using a mixer, a reforming reactor, a condenser, a methanol reactor, syngas recovery unit, a pump, and lastly a methanol purification unit.
My name is Natasha, and I'll be talking about the second chapter of our project, which is the process flow diagram. The diagram shown in the presentation currently is our proposed design for this project. The material balance for all units is calculated, and before going into details for every unit, this is the overall material balance of this whole project. The first one is the methanol purification unit. This unit carries about 80% of efficiency. Methanol and water has entered this unit, and one of the product of the overhead stream is being refluxed back to the same unit, while for the bottom stream, it is converted into a vapor flow before being returned back to the same unit. As the overhead stream is in liquid while the bottom stream is in vapor flow, the countercurrent will happen. Recycling this process is to increase the efficiency of the methanol production. Next is the syngas recovery unit. From the overhead product stream, 10% of carbon monoxide and hydrogen gas are being purged out before being removed as waste. And while 90% of the products have been recycled back to the methanol reactor. The reason for this recycling process is so that the carbon monoxide and also the carbon dioxide will undergo further hydrogenation as well as to prevent waste. We use 3 waste valves on the overhead stream so that we can control the flow rate of the stream. Next is methanol reactor. In this methanol reactor, formation of methanol gas will occur. Carbon monoxide gas will undergo hydrogenation process in order to form the methanol gas. The chemical equation is shown in the current presentation for the hydrogenation process that occur in the methanol reactor. The products from the methanol reactor will be cooled down until it reaches the saturation point of methanol. As for the condenser, 90% of water is removed through the bottom stream of this condenser. The reason for the removal of the water is for us to increase the heating efficiency for this process. This is due to water needing a large amount of heat energy as water has a high specific heat capacity. Last but not least is the reforming reactor. This reforming reactor is assumed to be 85% of efficiency. Methane will be react with excess steam to produce syngas and steam reforming will occur. Carbon monoxide also will react with water to form carbon dioxide and hydrogen gas. However, methane and water will not be completely reacted inside this reactor.
My name is Teoh. For the chapter 3, we have the vapor-liquid equilibrium diagram of mixture in D103 from the HYSYS. For PXY diagram, the temperature is fixed, and for our group, the temperature is given as 60 degrees Celsius. For PXY diagram, the bubble curve is above the dew curve, and for the region above the bubble curve represent the liquid phase, and for the region below the dew curve represent the vapor phase, and for the region in between the dew curve and bubble curve represent the vapor liquid equilibrium. This is an experimental graph that we found on the internet for the same component, which is methanol and water, and it shows a similar shape from the graph we obtained from HYSYS, where the bubble curve is above the dew curve.
Okay, so my part, I will explain regarding the phase envelope of mixture in D103. So we can have from the HYSYS, we can know the critical temperature of the mixture, which is at 239.4 degrees Celsius. Then we can know the critical temperature, which is 7,376 kilopascal. And then from the data of bubble point and dew point, we can see both pressure and temperature from bubble point and dew point are identical, which is here. So since the dew point and the bubble point curve have the same temperature and pressure, this makes the dew point curve and bubble point curve have the identical curve. So this happened due to the mole fraction of methanol is way larger than mole fraction of the water. Then since there's only one curve, which means this curve is separating between two phases, which is on the top is gas phase and the bottom is liquid phase. So at a given temperature, if the pressure increase, then the mixture will be in gas phase, and at the same temperature also, if the pressure decreases, then the mixture will be in liquid phase.
So now I'll be talking about the mole fraction of stream 3. So this is a process flow diagram where we have a cooler and a separator. Based on the article that we have read, the proposed condition for our stream 3 is 800 Celsius, 15 bar, and based on the calculation made in chapter 2, the mass flow rate is 108,723.4 kilograms per hour. Based on the trial and error in HYSYS simulation, to achieve 95% removal of water, it is needed to be cooled down to 98.7 Celsius, and the delta T, as you can see, is negative 701.3 Celsius. Therefore, this is the condition in separator, and this is the liquid and vapor composition that we have obtained for stream 3.
For the chapter 4, separation process 1, we assume that the phase from the previous S10 calculation, which is 71622.4 kg per hour, and the system is obeying Lorentz law, and the system pressure is at 65 kilopascal, which is between dew pressure and bubble pressure. And all the value we obtain here are from the question and also the previous calculation. For the feed stream, we calculated that the mole fraction of methanol, which is SF, is 0.876, and the mole fraction of water is 0.124. For the distillate part, we found that the mole fraction of methanol, which is SD, is 0.914, and for the bottom part, the number of mole fraction of methanol is 0.099. By using the Antoine equation, we found that the partial pressure of methanol at 60 degrees Celsius is 83.989 kPa, and for water is at 20.007 kPa. And since the system obeys Rod's law, we can calculate the relative volatility using the partial pressure of methanol and water, and it is at 4.197898. And since the relative volatility is greater than 1, separation process is possible. Then we calculate the bubble pressure of the system using this equation, and we got 76.05 kPa, and for the dew pressure is at 60 kPa. Then we will use the relative volatility to determine the equilibrium curve, and all the data here are calculated from the equation. After that, we need to determine the liquid composition at the feed stage. And since the system pressure is at 65 kPa, which is between the bubble pressure and dew pressure, fresh calculation can be used to find the composition of liquid at each stream. And after solving, we found that the liquid composition at the feed stage is at 0.159. Then we need to find the Q line by using this equation. And we found that the Q line equation is y equal to negative 0.189x plus 1.04. Then we will determine the minimum reflux ratio by using this equation, where Xd is the mole fraction at distillate and Y prime is the intersection between Q line and the equilibrium curve at the y-axis, and the X prime is the intersection between Q line and the equilibrium curve on the x-axis. After solving, we got the minimum reflux ratio as 0.07. After that, we need to determine the number of theoretical trays on the system. And we did 4 trials, which is from 1.2 minimum reflux ratio to 1.5 reflux ratio. And for trial 1, we used 1.2 minimum reflux ratio, and we got 4.8 theoretical trays from the graph. And for the second trial, which is at 1.3 R minimum, the number of theoretical trays we found on the graph is 3.3. And for the third trial, which is at 1.4 R minimum, the number of theoretical trays is at 3.8. And for the fourth trial, which is at 1.5 R minimum, the number of theoretical trays we found on the graph is 3.2. When it comes to choosing the most suitable system, we found that the optimum reflux ratio is 0.105, which is at trial 4, because it has the least theoretical plates, which is 3.2 plates. So the system will be the cheapest overall compared to the other 3 systems. And the estimated number of trays are 3.2 trays.